You already know that dinitrogen is abundantly available in the Earth's atmosphere and accounts for 78% by volume of it. Hence, dinitrogen is mainly obtained by the fractional distillation of liquid air. It is also the commercial method to prepare dinitrogen. The process of obtaining dinitrogen from air involves two stages. In the first stage, air is subjected to liquefaction. During liquefaction, a high pressure of 100 to 200 atmospheres is applied over dry air, followed by expansion through a fine jet. This process is repeated several times to obtain liquid air. In the second stage, the liquid air is subjected to fractional distillation. As dinitrogen has a lower boiling point, 77.2 Kelvin, than liquid oxygen, 90 Kelvin, it distills off first, leaving behind liquid oxygen. Thus, in this stage, dinitrogen is isolated from liquid air. In the laboratory, dinitrogen is generally prepared by gently heating equimolar aqueous solutions of ammonium chloride and sodium nitrite. Ammonium chloride and sodium nitrite react to form ammonium nitrite, initially as shown in the equation here. The ammonium nitrite so formed immediately undergoes decomposition to liberate dinitrogen gas. Dinitrogen can also be obtained by thermal decomposition of ammonium dichromate. The chemical equation corresponding to this reaction is shown here. Sodium azide or barium azide, when heated carefully to about 573 Kelvin, undergoes thermal decomposition to produce dinitrogen. The dinitrogen so produced is very pure. Have you ever heard this? Thermal decomposition of sodium azide, which generates dinitrogen, is used to inflate or fill airbags used as safety devices in some cars. Let us now look at some important physical properties of dinitrogen. Dinitrogen is a colorless, odorless, and tasteless non-toxic gas. Its vapor density is 14. Hence, it is slightly lighter than air. It can be condensed to a colorless liquid that boils at 77.2 Kelvin and can be solidified under high pressure to a white snow-like mass that melts at 63 Kelvin. It is diamagnetic in nature. It is slightly soluble in water. The solubility of dinitrogen at 273 Kelvin and 1 bar pressure is found to be 23.2 milliliter per 1 liter of water. It is important for us to study the reactivity of dinitrogen, as many of its applications are attributed to its reactivity. A molecule of dinitrogen consists of a triple bond that has a very high bond dissociation energy of 945.4 kilojoules per mole. Hence, dinitrogen is inert at room temperature. In other words, it is chemically inactive at room temperature, with the exception that it reacts with finely divided lithium to form lithium nitride. The reactivity of dinitrogen with lithium at room temperature is attributed to the highly active lithium. However, the reactivity of dinitrogen increases at higher temperatures. At high temperatures, dinitrogen reacts with elements from group 2, 13 and 14. It also reacts with hydrogen, oxygen and certain transition elements. At high temperatures, dinitrogen reacts directly with metals such as magnesium, calcium and aluminium to form the respective nitrides. It also reacts with hydrogen at high temperature and pressure in the presence of a catalyst to form ammonia, as shown here. Dinitrogen and oxygen react in equal volumes at a very high temperature of 2000 Kelvin to form nitric oxide, as shown here. Dinitrogen has several important uses. Being inert in nature, it has many uses in industry and other walks of life. For example, it is widely used as an inert atmosphere in iron, steel and other metallurgical industries. During the processing of steel and iron, dinitrogen prevents the formation of undesirable oxides. In metallurgical industries, it prevents the harmful effects of oxygen. It dilutes the activity of oxygen in natural processes such as combustion and respiration. It is used in the preservation of packaged food material. A large amount of dinitrogen is used in the preparation of ammonia by Haber's process. The ammonia thus prepared finds application in the manufacture of fertilizers. Dinitrogen is also used in the preparation of nitrolim, a mixture of calcium cyanamide and graphite, which is an important fertilizer. Liquid dinitrogen is used as a refrigerant to preserve biological material. It is also used in cryosurgery to remove warts and other skin lesions. Let us first look at various methods to prepare ammonia. Ammonia is found in traces in the atmosphere. The bacterial degradation of nitrogenous organic matter of plants and animals forms ammonia. The equation corresponding to the formation of ammonia from the decay of urea is shown here. In the laboratory, ammonia is generally prepared by heating an ammonium salt with a base such as caustic soda or slaked lime. Ammonium chloride, when heated with lime or caustic soda, evolves ammonia gas. The gas evolved is dried over quicklime. The dry ammonia gas is then collected by downward displacement of air. In place of ammonium chloride, ammonium sulfate can also be used, but not other salts such as ammonium nitrate or ammonium dichromate. This is because the anionic parts of the salts, nitrate and dichromate, oxidize ammonium ions to dinitrogen or nitrous oxide. On an industrial scale, ammonia is prepared by Haber's process. The constituents of ammonia, nitrogen and hydrogen combine in a ratio of 1:3 at high pressures and moderate temperatures to form ammonia. The reversible thermochemical equation corresponding to this reaction is shown here. From this equation, it is evident that the formation of the product is associated with fewer number of moles. In other words, the reaction proceeds in the forward direction with a remarkable decrease in volume. Also, it must be noted that the reaction is exothermic. Hence, in accordance with Le Chatelier's principle, high pressure and low temperature favors the better yield of ammonia. However, as the rate of reaction would be slow at lower temperatures, the reaction is carried out at an optimum temperature of about 700 Kelvin. Further, to accelerate the reaction, that is, to attain the equilibrium faster, a catalyst like iron oxide and a promoter such as alumina are used. Thus, a high pressure of 200 to 300 atmospheres, an optimum temperature about 700 Kelvin, and the catalyst iron oxide along with the promoter alumina are used to obtain better yields of ammonia. The flow chart of the manufacturer of ammonia is given here. Let us describe in short the process of manufacture of ammonia from the flow chart. Pure and dry nitrogen and hydrogen are mixed in a ratio of 1:3. This reaction mixture is compressed under high pressure of about 200 to 300 atmospheres in a compressor. Then, these compressed gases are let into a catalytic chamber that is fed with finely divided iron oxide with alumina at 700 Kelvin. Subsequently, the ammonia formed along with unreacted nitrogen and hydrogen gases are liquefied to obtain liquid ammonia. You know that the structural aspects of a molecule justify most of its properties. Now let us take a quick look at the structure of ammonia. You know that ammonia is a covalent molecule. The central atom in ammonia is nitrogen, which undergoes sp3 hybridization. Among the 4 electron pairs present in the 4 sp3 hybrid orbitals, one is a lone pair. On account of the presence of one lone pair, the geometry of the molecule is not regular, but distorted. Thus, the molecule acquires trigonal pyramidal shape. As a consequence, the bond angle is also less than expected, that is, 107.8 degrees. Now let us turn to some important properties of ammonia. Ammonia is a colorless gas with a pungent smell. It boils at 239.7 Kelvin and freezes at 198.4 Kelvin. You know that ammonia is associated with hydrogen bonding in both its liquid state and solid state. Hence, this factor accounts for the high boiling point and high melting point, that what is expected from its molecular mass. Note that liquid ammonia has high heat of vaporization. For the same reason, ammonia is highly soluble in water. Can you think of this? 1176 volumes of the gas can be dissolved in 1 volume of water at 273 Kelvin. The aqueous solution of ammonia is alkaline because it produces hydroxyl ions. Its ionization in water is represented here. However, the dissociation constant of ammonia Kb being very small, it is a weak base. You know that ammonia acts as a Lewis base as it has a tendency to donate its lone pair of electrons to a proton or other electron-deficient molecules. Owing to its basic character, it combines with acids to form ammonium salts. For example, when passed through a solution of hydrochloric acid, it forms ammonium chloride. An aqueous solution of ammonia precipitates hydroxides of metals from their aqueous salt solutions, such as ferric chloride and zinc sulfate, as shown here in equations 1 and 2. The ferric hydroxide formed in equation 1 subsequently gets hydrated to form a reddish-brown precipitate of hydrated ferric oxide. Talking once again about its tendency to act as a Lewis base, it forms complex compounds with transition metal ions such as copper, silver, and cadmium. An aqueous solution of ammonia combines with copper sulfate solution to form a deep blue color. The deep blue color is due to the formation of tetraamine complex. Similarly, the formation of a colorless diamine complex of silver ion is shown here. It forms complex compounds by donating its electron pair to the metal ions, thereby forming coordinate bonds. Thus, the formation of complexes finds application in qualitative analysis, by which these metal ions can be separated from other ions present in the given salt mixture. Let us now take a look at some uses of ammonia. Liquid ammonia is used as a refrigerant on account of its high heat of vaporization. It is used to manufacture fertilizers such as ammonium sulfate and ammonium phosphate. It is also used in the manufacture of certain industrially important chemicals, such as nitric acid, baking soda, and washing soda. You know that nitrogen forms a number of oxides that exhibit a wide range of oxidation states. The names of various oxides of nitrogen, their formulae, and oxidation numbers are listed in the table here. Note the oxidation states of nitrogen in all the oxides. You can see that the lower oxides include nitrogen 1 oxide and nitrogen 2 oxide, while the higher oxides include nitrogen 3 oxide, nitrogen 4 oxide, and nitrogen 5 oxide. We will discuss the physical appearance, structure, and chemical nature of each oxide, besides the most convenient method to prepare them in the laboratory. Let's start with nitrogen 1 oxide. Nitrogen 1 oxide, also called dinitrogen oxide or nitrous oxide, is usually prepared by heating ammonium nitrate gently to 240 degrees Celsius. Nitrous oxide is a colorless gas that is fairly soluble in cold water and the least soluble in hot water. Nitrous oxide is called laughing gas. Do you know why? This is because it produces hysterical laughter when inhaled, even in small amounts. Talking about its chemical nature, nitrous oxide is a neutral oxide. Nitrous oxide is a linear molecule that is a resonance hybrid of the two forms shown here. The bond lengths in the molecule are 113 picometers and 119 picometers. Nitrogen 2 oxide, also called nitrogen monoxide or nitric oxide, is prepared by the reduction of nitrite salt with ferrous sulfate. In this method, an acidified ferrous sulfate solution is warmed with a concentrated solution of sodium nitrite to get a pure sample of nitric oxide. Nitric oxide is a colorless gas that attains blue color when liquefied. It is sparingly soluble in water. Just like nitrous oxide, it is also a neutral oxide. Note the structure of nitric oxide, which is a resonance hybrid of the two forms represented here. The bond length is 115 picometers, which is intermediate between double bond and triple bond. From the structure, it is evident that nitric oxide is paramagnetic in nature due to the presence of an unpaired electron. Nitrogen 3 oxide, also referred to as dinitrogen trioxide or nitrogen sesquioxide, is obtained as a blue liquid when a mixture of nitric oxide and nitrogen dioxide or dinitrogen tetraoxide is cooled to below -20 degrees Celsius. You can see from the equation that dinitrogen trioxide is anhydride of nitrous acid. Also, it is evident from the reaction of dinitrogen trioxide with an alkali that it is acidic in nature. Let us take a look at its planar structure, which is a resonance hybrid of these two forms. Note the different bond lengths and bond angles in the molecule. Nitrogen 4 oxide, also called nitrogen dioxide, is prepared by heating lead nitrate at about 673 Kelvin. Nitrogen dioxide is a brown gas that is a mixed anhydride of nitrous acid and nitric acid. It neutralizes alkalis to form nitrites and nitrates. Hence, it is an acidic oxide. Examine the resonance structures of nitrogen dioxide. The molecule exists as a resonance hybrid of these structures. The molecule is angular in shape with a bond angle of 134 degrees and bond length of 120 picometers. Note the unpaired electron in the resonance structures of nitrogen dioxide, due to which it behaves as a paramagnetic substance. It is because of this reason that it attains a tendency to dimerize to a colorless dinitrogen tetroxide molecule that has an even number of electrons. At low temperatures, nitrogen dioxide associates to solid dinitrogen tetroxide. Take a look at the planar structure of dinitrogen tetroxide and make a note of the bond angles and the bond lengths in the molecule. These two oxides exist in equilibrium in a wide range of temperature, from minus 11.2 degrees Celsius to about 100 degrees Celsius. Below minus 11.2 degrees Celsius, only solid, colorless dinitrogen tetroxide exists, while above 140 degrees Celsius, only gaseous brown nitrogen dioxide exists. Nitrogen 5 oxide is also called dinitrogen pentoxide. It is prepared by the dehydration of nitric acid with phosphorus pentoxide. It is a colorless crystalline deliquescent solid that readily dissolves in water to give nitric acid. Hence, it is an anhydride of nitric acid. It neutralizes alkalis to give nitrates, as shown here. Thus, the oxide is acidic in nature. Here is the symmetrical resonance hybrid of these two structures. It is a planar molecule with two different bond angles and bond lengths as shown here. This symmetrical planar structure is observed only in its vapor state, which otherwise is ionic in the solid state. The ionic solid is referred to as nitronium nitrate. From the structure, try to answer this question on your own before looking at the solution. What is the covalence of nitrogen in dinitrogen pentoxide? From the resonance structures of dinitrogen pentoxide, it is evident that each nitrogen atom is bonded to 3 oxygen atoms by 4 covalent bonds. Hence, the covalence of nitrogen in dinitrogen pentoxide is 4. Nitrogen forms a number of oxo acids, such as hyponitrous acid, nitrous acid, pernitric acid, and nitric acid. Of these, nitric acid is an industrially important oxo acid. Let us first look at the various methods to prepare nitric acid. In the laboratory, nitric acid is prepared by heating potassium nitrate or sodium nitrate with concentrated sulfuric acid in a retort. The vapors obtained are condensed in a water-cooled receiver. On a commercial scale, it is prepared by Ostwald's process. The first step in this process is the catalytic oxidation of ammonia into nitric oxide. The nitric oxide is then oxidized to nitrogen dioxide, from which nitric acid is formed. Let us take a quick look at the process. First, a mixture of dry ammonia and air is passed through a catalytic chamber that is fed with preheated platinum gauze. The platinum gauze is preheated electrically to about 1155 Kelvin. It is a colorless liquid that boils at 84.1 degrees Celsius and freezes to a white solid at minus 41.55 degrees Celsius. Note that the specific gravity of laboratory-grade nitric acid, containing 68% by mass, is 1.504. In the laboratory, the nitric acid stored in bottles is usually yellow in color. Do you know why? Try to answer the question on your own before looking at the answer. Nitric acid undergoes photochemical dissociation to produce brown nitrogen dioxide gas. The brown nitrogen dioxide dissolves in the colorless nitric acid, turning it yellow. An aqueous solution of nitric acid undergoes ionization to produce hydronium ions and nitrate ions. On account of its ability to dissociate almost 100% to produce hydronium ions, it is considered a strong acid. On the other hand, the nitrate ions lend the acid solution its oxidizing property. Moreover, hot and concentrated nitric acid acts as a powerful oxidizing agent. You know that metals such as copper and zinc are insoluble in hydrochloric acid. However, these metals dissolve in nitric acid. The products formed depend on the concentration of the acid and the temperature. Concentrated nitric acid reacts with copper and zinc to give nitrogen dioxide. Dilute nitric acid reacts with copper to give nitric oxide and with zinc to give nitrous oxide. Certain metals such as chromium, aluminium and iron are rendered passive towards an attack by nitric acid. This is due to the formation of a thin layer of oxide on the surface of these metals. Noble metals such as gold and platinum are insoluble even in hot and concentrated nitric acid. However, these metals dissolve in a concentrated solution of nitric acid and hydrochloric acid taken in the ratio of 1:3. This solution is called aqua regia. Note that noble metals dissolve in aqua regia due to its ability to produce nascent chlorine. The nascent chlorine eventually forms a soluble complex on reacting with gold and hydrochloric acid, as shown in these equations. Concentrated nitric acid oxidizes nonmetals such as carbon, phosphorus, sulfur, and iodine to their corresponding higher oxo acids. The nascent oxygen produced from the dissociation of nitric acid oxidizes these nonmetals. You can see from the balanced equations that carbon is oxidized to carbonic acid, phosphorus to phosphoric acid, sulfur to sulfuric acid, and iodine to iodic acid. Let us now look at the familiar brown ring test. This test confirms the presence of nitrate ions in a given salt. Freshly prepared dilute ferrous sulfate is added to the aqueous solution of a nitrate. The test tube is then slanted slightly and concentrated sulfuric acid is added drop by drop, allowing it to slide along the sides of the test tube. A brown ring forms at the junction of the two layers. The brown ring confirms the presence of nitrate ions. You can see from the equation that the ferrous ion reduces nitrates to nitric oxide. The nitric oxide formed reacts with ferrous ions to form a brown complex. The brown color is due to the formation of a hydrated nitrosyl complex of iron. Let us now turn to the uses of nitric acid. Nitric acid is widely used in the manufacture of dyes and drugs, as well as explosives such as trinitrotoluene or TNT, nitroglycerine, and picric acid. The salts of nitric acid, such as ammonium nitrate and calcium nitrate, are used as important fertilizers. It is used in the purification of silver and gold. It is used in the laboratory as an oxidizing and nitrating reagent. It finds a major use in the pickling of stainless steel, etching of metals, and as an oxidizer in rocket fuel.